In this video, I want to do some examples of the closure property. At this point, you should have already watched a previously posted video with some more basic examples of the closure property, and in this video I want to just do a few extra ones dealing with some finite sets and also the set of rational numbers. So let's start with rational numbers. If we wanted to check if these numbers are closed under various operations, I think the best way to do this is to think of the fractional definition of rational numbers. So rational numbers are ones that can be written as fractions, where the numerator and denominator are integers, and where the denominator is not equal to 0. So it can be any integer other than 0. Alright, so then I want to just try some examples and see what's going on with these. So let's try to answer the question, are the rational numbers closed under addition? Closed under addition. Alright, so as an example, let's say we had maybe 1/3 plus 2/3. So I'm adding two rational numbers, and we get 3/3 or 1, and that is also a rational number. Okay, so that example seems to indicate maybe they are close under addition, but I don't want to stop there. I want to try a few other examples just to see if I can come up with anything a little bit different. So perhaps you want to try the examples, maybe a negative here, so like -7/5 plus 2/5. Maybe we'll do 3/5. Alright, and that would be -4/5. So that's still a rational number. What about if both fractions were negative? So if I had -7/5 plus -3/5, then we would have -10/5 or -2, and that's still rational. What about, now I know the denominator can't be 0, but what about the numerator? So let's say we try 0/3 plus 1/3. Okay, so that's just going to be 0/3, or I'm sorry, 1/3. If we had 0/3 plus 0/3, that's 0/3 or 0, that's still rational. Right, so all of these examples so far seem like perhaps the rational numbers are closed under addition. Now if I wanted to think about an explanation for that, what I would want to do is think about adding just two rational numbers in general, so I don't want to think about specific numbers, but maybe I'll use that expression that I have already written here, a over b, and I want to see what happens when I add another rational number, c over d. Alright, so things I know, we know that a, b, c, and d are all integers. A, b, c, d are integers, and I also know that that b and d are not equal to 0. Okay, so that must be the case in order for me to even be talking about adding rational numbers. So then I want to see what happens when I add these. Alright, well I would need a common denominator to do this, so I want to make these both fractions that are over the least common denominator, and without knowing what b and d are, I'm just going to use bd as the denominator. Alright, so a over b, I would need to multiply that by d over d. So I'm going to get AD in the numerator. And then CD, I would need to multiply that by B over B. So this is going to give me BC in the numerator. Alright, so now when I add these two fractions, this would be AD plus BC over BD. And then I just want to look at this answer and see, does this happen to be rational, or is there a way for that to be irrational, right? Or perhaps some other type of number. Well, I know that b and d are not equal to 0, so if you have two non-zero numbers and you multiply them together, there's no way for that to be a 0. Right? So that's going to help me guarantee that BD is not equal to 0. The other thing I need to check is whether the numerator and denominator are both integers. All right, so we would actually need to go back and rely on other closure properties. So what I'm really asking here is when I multiply two integers, is the answer still an integer? And I think we've talked about this one before, but if not, I'll say it now, and that the integers do have a closure property. So when you multiply two integers, it still stays an integer. And then how about the numerator? So not only am I multiplying two integers together, but then I'm also adding two groups of two integers together. So when you add integers, do you still get an integer? And the answer is yes. So that helps me know that this numerator is also an integer. All right, so I've met all of the requirements for a rational number, so this new thing that I've built, the sum of the two fractions, is always going to be a rational number fraction. All right, so all of that work helps to explain why the integers are closed under addition. So I can erase the question mark now and say that the rational numbers are closed under addition. What about subtraction? Are the rational numbers closed under subtraction? Well, now that we know that they're closed under addition, it's pretty quick to show that yes, they are closed under subtraction. So if I think about subtracting two rational numbers, notice that that I can just rewrite this as an addition problem. So I would think of this as that first rational number a over b plus negative c over d. All right? Or in other words, like if I had something like 5/3 minus 2/3, I can really think of this as 5/3 plus negative 2/3. Right, so we always can do that. That's the idea behind subtraction. It's really just adding a negative number. So since that's the case, subtraction is really no different than addition here. So that is going to give rational numbers as answers as well. So the rational numbers are closed under subtraction. All right, how about multiplication? If we have a rational number a over b times c over d, is that rational? Well, this is going to be ac over bd when we multiply, and a times c, so an integer times an integer, is still an integer, so numerator is an integer, denominator is an integer, and I just need to check and make sure that that's not 0. Okay, well, a non-zero number times another non-zero number is still going to be a non-zero number. So my denominator is an integer that's not equal to 0. So when you multiply fractions, this new fraction fits that definition, and that will always be rational. So rational numbers are also closed under multiplication. Alright, and then finally let's think about division. So if I have AB divided by CD, is that always a rational number? So again, A, B, C, and D are all integers, and B and D are not equal to 0. Alright, so to divide two fractions, we need that rule for division, and this would be the same thing as A over B times the reciprocal of C over D, which is D over C. So this is going to be AD over BC. Okay, so now is this answer a rational number? Alright, well I know A, B, C, D were all integers, so when we multiply, AD is an integer, BC is an integer. Okay, so the last thing I need to check, I need to make sure that the denominator is not 0. Alright, well what do I know about B and C? Well I know that B is not 0, but I don't know anything about C, right? Okay, so we know C is an integer, but I don't know whether or not this is equal to 0. Right? So if C is not a 0, then I don't have a problem here. But if C was a 0, there's a way for this denominator to actually be equal to 0. So in this case, the rational numbers are not closed under division. It's possible to get an answer that's not rational. And doing this process also helps me figure out what a counterexample would look like. It's going to be anything where C is equal to 0. So for instance, if I had 2/3 divided by 0/4, this is going to be 2/3 times 4 over 0, and that's going to be 8 over 0, which is not a real number, and it's certainly not rational if it's not even real. All right, so closed under division, in this case, no. Okay, so rationals are closed under addition, subtraction, multiplication, but not under division. I also wanted to take a look at a finite set, and this is simply a set or a group of numbers that just has a finite number of numbers in that set. So far we've mostly dealt with infinite sets, like the real numbers or the rational numbers, but we can check closure for a really small set as well. So this is a set of numbers, the braces indicate a set, and there are only two numbers in the set, -1 and +1. And we want to check if this set is closed under some of the different operations. Okay, so closed under addition, we'll start there. So in other words, if I add numbers in this set, is the answer always in that set? Or, right, so that would be closed. Or is there a way for an answer to leave that set? Is it an open set? So let's check, and you can just start adding things together here and see what kinds of numbers you get. So for example, -1 plus 1 is 0. So already I have a counterexample. So this is something that's not in the set, so that tells me that the set is open. And let's just try a few others to see what other types of counterexamples you might come up with. You can also add numbers to themselves. So we could do -1 plus -1, and that's -2, so there's another counterexample. And then 1 plus 1 is 2, and you could use that as a third counterexample. Okay, so the set is not closed, it is open under addition. Okay, let's try division. Closed under division. We'll see if that's the case. Alright, so we could do -1 divided by 1, and that's -1. We could do, I could change the order around, so I could try 1 divided by -1, which is still -1. And I could divide each of these numbers by itself. So -1 divided by -1, or 1 divided by 1. So notice in all four of these cases, the answers turned out to be in the set, and I've also checked all possible combinations of numbers in the set. So there are no other examples I could use as counterexamples. I've checked all of them. So this tells me that that the set is closed under division. And you would try the same thing if you wanted to check subtraction and multiplication. Right? So try some different examples, see if you think the set is open or closed. And then finally, here's another set, the finite set consisting of 0 and 1. So let's do, we'll do subtraction for this one. So is this closed under subtraction? So I could try 0 minus 1, I could try 1 minus 0, 0 minus 0, or 1 minus 1. And those are the only combinations using subtraction that I could get with this set. So I'm just going to check all of the answers here. And we get -1, 1, 0, and 0. So it almost looks like this would have been closed, except we do have a single counterexample here. 0 minus 1 is -1, so this set is not closed under subtraction. And I will leave it to you to check the other operations, addition, multiplication, and division.